All right. Hello, everyone, and thank you for joining us today. My name is Megan, and I'm going to be your host for this session, which is Eliminating Redundancies and ETL with Iceberg Tables on Snowflake, presented by Nikita Pestrov of Zello. So we've got a couple different chat options. If you look at your little chat tab on the right, there's an opportunity there to just join the general conversation. You can drop your LinkedIn URL to connect with fellow attendees, tell us where you're from, any comments you have about the session. And then if you have any questions for Nikita, drop them in there. We're not sure if we'll have time to get to them, but if we are surprised with some extra time at the end, we'll go ahead and do that. But that's it for all of the housekeeping. And with that, Nikita, I will hand it over to you.
Thanks, Megan. Thanks, everyone, for coming by my session. I hope you're enjoying the summit so far. I know it's been great. There are tons of great sessions out there and learning materials. And today, I would like to present on this topic that's dear to my heart, on how we eliminated a lot of redundancies in our ETL process with Iceberg tables. And I don't want to show some super difficult technical stuff. I think the goal of my session today is to show that Iceberg tables are a very high leverage technology that you can use with pretty minimal efforts to set up as a part of your data platform and start reaping benefits today and be prepared for the future. And I will demonstrate that how we were able to reduce the cost on storage for more than 20% with a fairly minimal setup at a pretty high volume. So that was a high impact activity for us. So to start, I want to bring in some context of where we have implemented this. So I work at Zello as an analytics engineer. So Zello is a walkie-talkie company. What we do is we provide voice communication to frontline workers. And it happens around the globe. So we need to support a 24/7 access to our services and provide the best possible reliability across a wide suite of our client apps. And to make that better, at the core of it lies a lot of product analytics. So we gather analytics about more than 100 million users, and that takes a lot of compute, a lot of storage. So we're always focused on how we can optimize this flow to make our product even better. Because we support a wide array of these big customers who rely on us as a reliable partner in communications. So part of that is just getting in that huge amount of data. For us, it's more than 500 million events, analytic events per day. And this is just one of many sources that we work with. And we, being a pretty lean team as a data, I'm the only analytics engineer in the team, we rely a lot on the modern data stack and the technologies around that. So as a part of that, we rely on Snowflake as our key data warehouse, where we manage all our data sources, we transform data, we run AI, machine learning on top of that, and it's just like the key storage of all our data. So we want to get these 500 events from analytics to Snowflake. Because then what we do with it, we analyze it internally to drive product development. We provide this data to our external users through dashboards or data products. So this just lies in the core of it all. And we do it in Snowflake. But the data that powers this key part of this all is Google Analytics or Fire-based data. So this is the data collected from clients, from the web apps, from mobile apps, and it flows to Google. And since this is a Google solution, it initially lands in BigQuery. So this mostly consistent stack of Snowflake and dbt on top of that gets a little bit mixed up with the source coming to BigQuery. And as I said, it's a pretty big amount of data, so we need to find a way to reliably bring the data from BigQuery to Snowflake so that we can make our analytics run on top of that. And this is where Iceberg will come into play. So we've been doing this process that might be familiar to some of you, where we have BigQuery as our source to which the data lands in BigQuery tables, and they are partitioned by date, and each date we have like 500,000 new events, and we then need to batch load to Snowflake so that we can run our transformations on top of that. And there is this pretty straightforward pathway that we have been utilizing for long. So we take the data in BigQuery, we then run a batch export job that takes it and loads it into something that's interoperable and that can be loaded by Snowflake, but maybe by something else. And it does it back into JSON. So we produce a lot of JSONs, load them into cloud storage bucket. And once it's there, we use a stage in Snowflake that sees this data and then runs with Snowpipe. We catch these new files once they are there and launch tasks to unpack the data. And once it's all said and done, we get this 500 million events or rows, each of them is a single row, come from BigQuery to Snowflake, where we can finally merge that with all the other data like billing and some other components that we rely on, like support cases, into a single unified data models and transform them with dbt. So it's all good and well, but we've been thinking that there are some redundancies in that, and maybe we can do better than this flow with data exports. So what are those redundancies that we have identified? They are like two of them, broadly speaking. It's about storage redundancy and compute. So for storage, you can obviously see that, and this was the big for us, is that we first export the data from BigQuery to Google Cloud Storage, where we load it there and it sits there in JSONs. But we cannot access it straight away. We need to just ingest it to Snowflake through a Snowpipe and create more or less the same representation of the raw data, but in two places, in Cloud Storage and in Snowflake. So that produces twice much data than is actually needed. And while it's not that much incrementally, you see it's around 5 more terabytes of data per month. But since they are accumulating, you are integrating over this 12 month of data, you get 5 more terabytes of data this month, 5 more next month, and in the end, you get 9 more K incrementally just on storage alone that is not needed. And we're incurring these costs in Snowflake because we already store it in Google Cloud Storage, but now we also do it in Snowflake. And we were unhappy about it. It also introduces potentially two sources of truth. So we have this raw data in Snowflake, we also have it in cloud storage, and we hope that it's always the same and that we never have to read it again. But you don't know that it's the same because physically it's two separate, absolutely not connected set of objects. So that was one, storage. The second one is the compute. And compute-wise, we end up going through this unnecessary intermediate step where in BigQuery, we have this beautiful table with structured columns that have all the properties and entities in them. But then we lose all that partitioning, we lose all that structure and accessibility of each record once we turn it into a JSON that just sits there in the Google Cloud Storage bucket. So we do some compute to transform it from a table to this JSON. And similarly, then we need to unpack it. We just first load these JSONs to raw data table, and then we access these JSONs, these variant objects, these unstructured objects, and turn them into some cleaner version of them that we can then use as a source. Again, going through this intermediate step was not great. And we also could not use this cloud storage data for anything else. Like we were really hoping that we only read it once in this ingestion step, but we didn't really foresee how we could later use some Python process or some AI model to run on top of this cloud storage data, because it lies in this very inaccessible format in JSON that's hard to analyze, hard to query, and there's no metadata about it. And that's where Iceberg table came to our rescue. And I got inspired to try this last October at Coalesce, at one session when I was like, okay, let's see if we can turn the hype about Iceberg tables into something tangible that we can use. So I guess most people here know what Iceberg is, but just as a reminder, there are multiple, it's like an open standard for tables, and you have multiple layers there. You have the data layers with data stored in Parquet files, nicely accessible by columns and partitioned there. You have a metadata layer, which stores information about which files are available, which files store which rows, which partitions are there. It maintains the history of the schema evolution and of the addition and removal of the rows. And then there is the catalog. An Iceberg catalog can take different shapes and forms, but its goal is to expose this metadata to an SQL engine. For us, it's a Snowflake engine. It needs to know which tables are there, how to access them, what's the latest metadata, and how to find it. So with all these components, somebody needs to maintain that. And luckily for us, both the Snowflake and BigQuery support Iceberg. So we decided to let's see if we can make it work. So the natural evolution of the pipeline I showed earlier with Iceberg table looks like this. You get your source BigQuery table that's out there, and then you want to insert that into an Iceberg table that's in between, and then just access this Iceberg table in Snowflake. This, while looks simple, and it is indeed fairly simple, raises a few questions about what is your Iceberg catalog? Who manages that table? Where do you store this table? So we needed to answer all these questions, but often you don't have that much of a choice. For us, in this example, we didn't have much of a choice. The reason is, there are two places who can manage this table. It can be a BigQuery-managed table or a Snowflake-managed table. We went with BigQuery managing this table because it is the one that maintains, that will be writing to the data. And I think it's pretty often is the case that you want to delegate the management and the catalog of your Iceberg table to a platform that writes to this table more often than not. So in our case, BigQuery is the writer and Snowflake is the reader. So BigQuery introduced the support for managed Iceberg tables last October, just a few months ago. And we went straight on and implemented this. So the way it works, you create a managed Iceberg table on Google Cloud Storage, and BigQuery is responsible for maintaining the structure of the folders there, the Parquet files, and the metadata. And once you do that, you can then expose and bring this table into Snowflake by providing Snowflake information about how to access this table, where is the data stored, where is the metadata stored, and I'll cover this in more details now. But basically, yeah, this is the kind of architecture we ended up with, and we made it to production last November. So we've been running it for a few months, and I have some highlights to show like how successful it has been for us in this 4 months now. So let's dive straight up to see what's going on in different stages of this process. So first, we need the data to be loaded into this Iceberg table. For us, as I said, it's a daily batch process. So the data is ready at the end of the day in BigQuery. And once it is, first you need to set up this table. It's fairly simple. you create a BigQuery connection that connects to this cloud storage bucket that you also need to create. And then this allows BigQuery to run commands against this table. You create a table, and you cannot create a partition table, but you can create a cluster table. And that's what we did. We created a cluster table by date and by scope. Basically, we have different types of events, and we wanted to be able to access some of them independently of the other. So when you look in advance, you need to plan your partition as always as you do. So once you do that, BigQuery establishes this folder structure in your bucket where you have data with Parquet files and metadata with your JSONs, manifests, metadata of where each Parquet file lies and what is there. And the manifests are the ones which say, hey, this Parquet file has this part of the information, and it shows like this minimal, maximal bounds of date and a scope for us. So we set it up, and that was fairly easy. The second part is how do you access this data in Snowflake? So Snowflake, of course, has their own Snowflake-managed tables, but that was not the case. So this was a little bit more complex. You need to set up an external volume, which links this Google Cloud Storage and introduces this as a volume that Snowflake can access. Then you run this catalog integration. Catalog integration is this entity which tells Snowflake, hey, these are the tables that are there in this volume. This is what metadata they have inside. And the catalog option, there are different types of catalogs. There is a REST catalog, but here we have to resort to the simplest version of a catalog, which is just stored in a bucket in Google Cloud Storage. We don't have any API other than regular Google Cloud Storage read and list API. So we need to resort to that. And once you set up this Iceberg table as external managed Iceberg table in Snowflake, it starts to look more or less any other table in Snowflake. Like my data analysts don't really see that this is an Iceberg table. You can see all the metadata, all the stats, the amount of data, all the columns, and it even supports pruning of your queries based on Iceberg partitions and Iceberg clustering, and I'll get back to that in a sec. But that was crucial for us because we didn't want to scan the whole table each time we just get one more day of data, and that's supported in Snowflake. What was not supported was a dynamic table on top of that with some views, and stream. So actually stream is supported, but with dynamic tables there are some elements you need to be cautious about. So yeah, we set up this table and we were ready to go to do this daily loads of the data. Sorry, I'm having trouble switching my slide. Megan, yeah, if you could, yeah, here we are. So here, I wanted to dive a little deeper into what the table actually looked like because it felt initially pretty opaque. But I think it's one more great thing about Iceberg tables is you can actually easily debug what's going on, see your data, unlike like Snowflake table where it's just micro partitions out there. You can see what it looks like by just accessing your bucket with the data. So what we have here are Parquet files, as I said, with the data, but then we have this daily metadata JSONs that contain the link to the latest manifest, storing information about what data was added to the bucket. And sadly, Snowflake is not able to automatically maintain and refresh the state of this table. So if you just run in BigQuery and insert and export metadata, it will add new data and new metadata to your bucket, but Snowflake will have no idea about it. If you run some query to select data from it, it will reference the old version of this Iceberg table. So it's on you, a developer, an engineer, to maintain that link. And it's fairly easy. The way we did it is we have a stage that we can access, and we have a little script that lists all the files in this metadata stage directory, finds the latest file based on the created date, like file modified date, and uses that to update and refresh the Iceberg table metadata to provide it, to tell it, hey, this is the latest version of my table, please use it. And from that, again, nothing, it doesn't run any expensive computation once you refresh this. It just updates the link. So any following query after that will be able to access the latest version of your table. So I've been told that both BigQuery and Snowflake are working on a better version of that, like exposing this latest JSON, but so far you need to be the one who maintains that. And yeah, as I said before, once the data is loaded to Snowflake, it looks like any other table more or less. And we use dbt a lot to support our data transformations on top of Snowflake tables. So in Snowflake, this table looks like any other table, except for this new field, structured object. Usually we have this semi-structured or unstructured, like arrays or variant or objects. Here, this is the cool thing about this, is that we have these nested structures which have specific type as keys and values, and you can have more expectations about that. But you can only see that in Snowflake. dbt doesn't show this nested structure of your column. So I'm waiting for that support to happen. It'll be great. But otherwise, you see it now becomes just a part of this lineage graph in our dbt transformation stack. And yeah, analysts don't even notice that there was a change. So yeah, with this change, fairly simple. It took me around a week as a solo engineer to kickstart this, and then a couple of weeks of some tweaks and adjustments allowed us to go from this data duplication, resource duplication, to a streamlined source of truth. And we're launching a lot of AI initiatives this year, so we're considering this Iceberg table as a potential place that not only us as data team can access in dbt, but other tools can access with DuckDB or custom Python processes running the data science jobs. We can all reference this single table that's out there. And this gives us a lot of freedom. And to be, transparent, this now has been running for 5 months for us since late October, and it has generated more than 30 terabytes of Parquet files in this cloud storage. It's around 1 million files, and this might feel overwhelming, but that's similar to what's going on behind the scenes in the regular Snowflake table, but just now you can see that. And it's important to properly partition and cluster your data beforehand so that you don't need to redo that later on. And here I'm demonstrating how Snowflake is able to effectively prune this data. So you can see that we have more than 750,000 partitions total. But if we just filter out by this event date, we can see that it is able to recognize that there is clustering in our table. So each file only contains data for this particular date, and it can easily find that out using the manifests files and only scan the relevant files. So that was a huge relief for us. Snowflake thus says that there is limited support for pruning. So it was a bit of a gray space. We were not knowing for sure what we're getting into, but it's been working as expected here. One element, though, that I would suggest to keep in mind is that we do see, when we analyze the access patterns of this cloud storage bucket, we do see that the same file, the same Parquet file, is sometimes egressed multiple times, meaning that in one query, even though this file only has like a subset of the data, something within Snowflake makes it so that it's trying to download it multiple times. So I'm still interacting with Snowflake to find out what can be the root cause of that and if there is a pathway for exploration. And this might not be a problem for you if your Snowflake account and your data are in the same cloud platform. So if your Snowflake is in Google Cloud, then you're not incurring any egress costs, so that's all great. But if you are doing some cross-platform stuff, like your Snowflake is in AWS and your data, your bucket is in Google Cloud, then you might incur some extra egress. So be conscious about where you put your data and what is the most likely access pattern. So you might want to even write into a different platform if you're only writing once, but you're reading it many times in the future. So that's something to keep in mind. And that's, I guess, one of my key takeaways from this process is that you can actually start pretty small. And I think it is important to start small. Like, you don't want to go all in on Iceberg and replace all your flows and be overwhelmed with the amount of technology and changes. For us, we didn't start small volume-wise, but we did start small in terms of the scope and where we have deployed this technology. But at the same time, we chose a pretty high leveraged and high impact location, the one that where it's pretty limited in the amount of sources, but it generates the most data and is the key for us. So we were able to get a lot of benefits from cost reduction and compute reduction. As I said, more than 20%. We reduced a lot of storage costs, we reduced a lot of Snowpipe costs in transformation and BigQuery costs. So start small, finding this right spot to implement Iceberg and learn how it works. It's also important that not all directions work and are the same. So there is this pathway from BigQuery to Snowflake is pretty straightforward. But from my exploration, for example, Snowflake to BigQuery might be trickier. So you need to really think about what's your writer, what's your reader, how you play out this hub. And yes, plan for data egress and your access patterns. Nothing new here. We always need to think about when modeling our data, how we're going to access it. But here, it's important not just from the structure, but also from the location and the interactions between services. So with that, I encourage you to start out. There's never a better time than today to explore Iceberg while you're inspired by the whole summit. And I'm really grateful for the organizers of this event and happy to answer all your questions. Feel free to add me on LinkedIn. And yeah, thanks.
Awesome. Thank you so much, Nikita. We do have a couple questions and we got a little bit of time, so I'm just going to dive right in. So the first question is, how are you maintaining the Snowflake tables when any new data is added?
Yeah, that's a great question. So for us, I guess there are two parts to that. There is like new data by itself is when it maintains the same structure is pretty simple. So that's how it works for us. We ingest new data from BigQuery to this table. And as I said, Snowflake doesn't see it automatically. Snowflake doesn't know that the new data was added because there's just some Parquet files out there. So what you need to do is you need to update the reference to the latest metadata of the table. So we do this with this custom task, which finds the latest metadata file and tells Snowflake, hey, reference that. Once we do that, Snowflake knows that there are new files and it can run queries efficiently. So that's one, pretty simple. A more complex one will be with the schema evolution, where not just new data, but new data types and new data fields are added to the table. That's also supported in Snowflake externally managed tables. Again, you update your reference to the metadata, you can see the new columns, and you work from there. So that case is supported. Thanks for the question.
Oh, yeah, great. So one more here before we wrap up, and it's a bit long, so if you need me to reread it, let me know. But it says, what does activity on these Iceberg tables in Snowflake look like? I believe you will be able to see in a Snowflake query history all read operations and any data movement from Snowflake to DBT, etc. But how is the data that is inserted, or what does the data that is inserted in Iceberg look like? Do we get the user as some service user, or any copy into Snowflake operations scene? Hopefully that makes sense to you.
Yeah, that's a good question. Let me bring back the slide maybe to show some of that.
Pop them up there.
Yeah. So as I said, there is a good and bad of that. So good is that you can actually see a lot of how your data is stored with Iceberg tables. So we can see the full data in the Iceberg, how it's stored, looking at the cloud storage. So we can inspect the Parquet files themselves and see that, hey, this is what's inside of them. You can read them with any Python library and see what's inside. You have the Avro files, which contain the metadata about which files have which boundaries of, this file has data for April 1st for this event scope. So we can inspect that and validate that. And you have your metadata JSON files, which tell you what's the structure of the table. So you can inspect that, but then you're asking more how do you see the operations? What about the data copying? So just having the Snowflake table reference this Iceberg table does not make any copy on itself. Any interaction with this data only happens when you run your select queries, or some, say for simplicity, you run a select query which wants to some column over the last 5 days. So when you run that, this is where Snowflake is raising that manifests in order to identify which files to access. It downloads that file to some Snowflake environment and unpacks them and reads the data. And this is where it becomes less transparent. So what you can see from the Google Cloud Storage side, you can enable access logs to see when a certain file has been downloaded or egressed. So you can both monitor your costs, but you can also see what is Snowflake trying to do behind the scenes, which files it downloads to run a query. So you can run a query and you can see which files were accessed when that happened. Then within Snowflake, you get your regular stuff. You get your query, you have the profile, you can see how it pruned something, but you don't see which files it accessed during the query. That's still not exposed. Recently, Snowflake added an ability to list the files which are out there within Snowflake. So you can run a command, system files list something, which will tell you the full list of the files which go into this Iceberg table. And then you can try to, I don't know what you want to do with that, but you can see that. You can see Snowflake's representation of that. But I do agree that there is more to be done in terms of seeing which files are being accessed during each query within Snowflake. That's still not out there. And in terms of users, yeah, in order to connect, to make Snowflake be able to read that data in Google Cloud Storage, you need to create a service account. Like you need to grant access to Snowflake's service account so you can read the data. And then you can see, as you always can with any cloud identity management, you can see what this user has been doing, what operations it ran. Yeah, so there's that. But it's important to know that like a lot of costs incurred will be on your storage side. So for us, we have shifted this. We reduced the costs of storage from Snowflake and put them just on the Google Cloud side. And like one more note, like we don't see any significant cost of like read operations, even though we are using these hierarchical buckets which produce higher speed. The main cost we incur is still egress from cloud storage to AWS. I hope that answers that question.
Awesome. That was a very thorough response. So yeah, I hope that answered the question for them as well. Well, with that, we're going to go ahead and end this session. I've dropped Nikita's LinkedIn in the chat there if anyone wants to connect with him on there. But don't go away. We do have one more round of tracks after this. And this track, specifically, we are going to have building a batch stream unified lakehouse on Apache Iceberg and Tencent Cloud with Jinsong Zhu from Tencent. That will be next. And then if that's not of interest to you, we've got 3 other tracks. You can just click into the agenda and pick what interests you most. And then after this next round, we will be closing the event with a replay of the closing keynote from yesterday's live event here in San Francisco. So you don't want to miss that. Nikita, thank you so much for being here. This was great. We got a lot of good questions. It looks like everyone really enjoyed what you brought to the session. So really thankful to have you here. But everyone enjoy the rest of the event and we'll see you in the closing keynote.
Thank you so much. Thanks, Megan. Thanks, everyone, for coming. Have a great day.